Okay, this is a presentation on the night sky, and at several points in here, I'm going to pause and maybe ask you to pause the recording yourself and think about some of the questions that I'm asking. The more actively engaged you are with this and the harder you think about some of these questions, the more you'll remember it and the better you'll be able to rattle it off when you come to a question like this on a test. Here's something. For starters, imagine that you stay up for a full 24-hour period from 5 a.m. one morning to 5 a.m. the next morning. This may take a lot of imagination. You could bump it to 7 a.m. one morning to 7 a.m. the next if you want. The weather's perfect for the entire 24-hour period, maybe similar to what we're experiencing right now, with not a cloud in the sky. Write a detailed paragraph describing what you could observe in the sky during this 24-hour period. See if you can pause and do the writing right now. Are you back? Okay, I'm going to go forward here. There's an old song by the Beatles called "The Fool on the Hill," and in the chorus it's got the line, "See the sun going down, but the eyes in his head see the world spinning round." If you want to give yourself a strange little twist, watch a sunset sometime this week, and while you're watching the sunset, stop and think, the sun is not moving, the thing I'm standing on is rotating, and that's why the sun appears to drop down. It's because my western horizon is rising up. Try to do that. It's a nice little twist. Okay, I'm going to show you a series of pictures here. This one I'm pretty sure was taken at Arches National Monument in Utah. My only experience being anywhere near there, I drove by it one hot, blistering hot day. I was driving from Boise to New Mexico, and I was going to stay overnight at Arches National Monument, but when I went by there about 6 o'clock at night, it was still well over 100 degrees. So I went to Moab and stayed in an air-conditioned hotel. I wimped out. Anyway, there's something. And this is something that you get if you take what's called a time exposure picture. You aim your camera in some direction and you do what's called opening the shutter, and you just keep gathering light for a long period of time. And you get pictures that look like this, or this. I'm not sure where this one was taken, but it's pretty spectacular. Lots of stars. And we get those circular things showing up there too. Okay, here was a picture taken on, I'm pretty sure, the big island of Hawaii. A time exposure picture. In this case, the camera probably wasn't set quite so sensitive to light as one of the earlier pictures. But you see stars moving around in particular directions. We're going to want to start using some terminology. And terms that I want you to become very familiar with are celestial sphere. Read about these in the textbook. The celestial equator, the north celestial pole, and the south celestial pole. I'm not going to define all of them here, but we'll start using those terms as we go along. The point in the sky that that yellow arrow is pointing to, the center of all the star trails, is the north celestial pole. And the star Polaris is very close to that point. In fact, that bright smile that's right underneath the tip of the arrow is the track of Polaris. Polaris is actually a little less than a degree away from the north celestial pole. So here's a kind of who's buried in Grant's tomb question. If the point in the center of the star trails is the north celestial pole, which direction is the camera aimed? Well, it's north. Okay, that's how you see that. Now, how long was the camera exposure? Stop and think. Why are we seeing those star trails? Why do they exist? How long would it take to make a full circle? If you say a day, you're right. But if you say a day is 12 hours, that's not right. It takes almost 24 hours for the Earth to turn on its complete axis, one complete turn. It actually takes 23 hours and 56 minutes. The difference from 24 hours is something we'll address later in the quarter. But for now, just round it off to 24 hours is how long a full circle would take. Does it look to you like those bright star trails you see, either that one for Polaris there, or there's a fairly bright star up above, are a little less than a full circle, or a little less than a half circle, excuse me. And if it takes 24 hours to make a full circle, it would take 12 hours to make a half circle. And so the camera exposure must have been a little bit less than 12 hours, maybe 11 or 10 hours, something like that. Not quite the full 12 hours. Can you make a general statement about the direction of the curves the stars follow? Which way are they moving? Right. Well, here's how you can figure that out stepwise. First, from the north celestial pole, if you drop straight down to the horizon, you're looking north. That's the direction north. If you're looking north, east is in that direction. Right above the word east is probably to the northeast. Where does the sun rise? The sun rises in the east. Those stars over there in the northeast are coming up from the horizon. They're traveling in that direction. Well, if they're traveling in that direction, stars up there must be traveling in that direction also. Stars down there, though, they're traveling in a way in the same direction. But if they're above the north celestial pole, they're moving from right to left. And if they're below the north celestial pole, they're moving from left to right. But they're all traveling in a common direction around the north celestial pole. And if all you ever do is look at a digital watch, you might not know this, but they're moving in a counterclockwise direction, okay, opposite the direction that the hands on a clock move. Is your general rule that they move in counterclockwise circles good only for the north celestial pole? We'll think about that and come back to it here. For that bright star trail right there, what is the start and what is the end? And I'll let you think about it. See if you can figure it out with that general direction that the star is traveling. And for this bright star trail, the track of Polaris, what is the start and what is the end? So be thinking about that. Let's go to the southern hemisphere. Okay, suppose this picture was taken in Australia, and it was, and the camera is pointed south. How long was the camera exposure here? Stop and think about that. How long would it take to make a full circle? What fraction of a full circle are you seeing? And if you can't quite figure it out, you can ask a question in the discussion forum that we'll set up in class. Can you make a general statement about the direction of the curves the stars follow here? Well, let's go through the same reasoning or similar reasoning that we went through for the northern hemisphere. In the southern hemisphere, you'd be looking at the south celestial pole, and if you drop straight down from that to the horizon, you're looking south. If you're looking south, then west is over that way. The west is where things set. And that doesn't matter where you are, things set in the west. So those star trails over there on the right side of the picture are dropping down toward the horizon. The star trails over on the left side of the picture are coming up from the horizon. And which direction is that with respect to a clock? They're clockwise in the southern hemisphere. Interesting. Okay, for that bright star trail there, what is the start and what is the end? Remember, these ones are going clockwise. Okay, you should be able to label those things. And for the bright star trail here, which is broken up a bit by the branches of the tree, what is the start and what is the end? And remember, it's traveling clockwise. So you should be able to figure that out. So if looking at stars near the north celestial pole, you see counterclockwise circles. And looking at stars near the south celestial pole, you see clockwise circles. What do you see for stars in between? Those circles get larger and larger as you get farther away from either the south celestial pole or the north celestial pole, and you don't see the full circle. You only see the part that's above the horizon. And eventually, if you're coming south from the north celestial pole, the paths you see will stop being parts of circles, and one of those paths is going to look like a straight line. And then if you keep going south, they'll start looking like parts of circles again until you get down to the south celestial pole, which we can't see from Moses Lake, but they'd be smaller circles. That point where that looks like it's traveling in a straight line is the celestial equator. And we can see stars on the celestial equator here in Moses Lake. We'll come to that in a few days. The celestial equator, actually for people everywhere on the earth, it rises due east, it sets due west, and the stars on the celestial equator appear to travel in a straight line. It's not straight over your head unless you happen to be on the Earth's equator, but they do appear to travel in a straight line. Time for a secret ballot here. Don't let anybody else see your vote. And pause and think about this here. Moses Lake's latitude is about 47 degrees north latitude. And from here you look straight north and you see a star very near the horizon. A short time later, say 10 minutes, you notice that the star has shifted its position slightly. Which way did it move? A to the east, B to the left, C up, or D, down? Now, a key thing in this question is 10 minutes. All of those arcs we looked at were hours long. So only 10 minutes, not going to be much of an arc. You can pause this and think about it. And let's go through figuring out the answer. Okay, we're looking north here. This isn't from Moses Lake, this is from Hawaii, but that's okay. We can still imagine the same effect. Okay. Now remember, stars in the northern hemisphere go in a counterclockwise direction. So that red streak up there was the path of a star that is above the north celestial pole at this time. A couple of stars below the north celestial pole at this time travel like that. Okay. So we were told it was a star very near the northern horizon, which kind of sounds like that bottom red arrow that we have here. That's pretty near the northern horizon. And in a short time, that's the direction it might go. That's still probably too long. Cut that arrow to a third of its length, and what direction will it look like the star is going at that time? To the right is east if you're looking north. So you can repeat this and think about it a little bit harder. It's a good question. Okay, here's an interesting question. Consider the situation shown below, in which the sun and a group of constellations are shown at sunrise. And the sun rises in the east. Whoops, I thought I put an arrow on there. It's missing. Oh well. Look over there on the left side of the picture, and there's a kind of a smudge on the horizon that's supposed to represent the sun. That's toward the east. And now the sun and the constellation are shown 8 hours later. Okay, is this later picture correct? Explain your reasoning. You may see the sun up there just to the left of Aries. So think about this. You may want to flip back and forth between this part of the video here. But here are a couple of students having a debate about this. Student 1 says, we know the sun rises in the east and moves through the southern part of the sky and then sets in the west. 8 hours after sunrise, it makes sense that the sun will have moved from being on the eastern horizon near the constellation Cancer to being high in the southwestern sky near the constellation of Aries. Student 2 says, you're forgetting that some stars and constellations also move from the east through the southern sky and to the west, just like the sun. So the sun will still be near Cancer 8 hours later, so the second drawing is incorrect. It should show that the constellations have all moved like the sun. So Cancer would also be located high in the southwestern sky, with the sun 8 hours later. So do you agree or disagree with either or both of the students? Explain your reasoning. Check your answers with another group. Actually, this is a group activity in class, but check your answers with somebody else in the class if you know anyone.